All right, today we are finally getting to the question that most of you have. How on earth do you find an Euler path or an Euler circuit? So we are going to start with Euler's circuit theorem. If a graph is connected and every vertex is even, then the graph has an Euler circuit. If a graph has any odd vertices, it does not have an Euler circuit. So we have three graphs here. We want to look at these three and decide, do they have an Euler circuit or not? Okay, so we have our first graph here. No, this one is not going to have an Euler circuit because it is disconnected. If a graph is disconnected, it automatically does not have an Euler circuit or an Euler path, but we'll get to that in a few minutes. Okay. Graph 2 and graph 3 are both connected, so that's good. Now we need to go through and look at the degree of each of the vertices. Okay, so this is 2, 4, 3, 3, 2, 3, 5. Well, this one has 4 odd vertices. So we do not have an Euler circuit. Let's check this last graph here. The degree of each vertex, this is 2, 4, 4, 4, 2, 4, 6. So yes, we have a connected graph, and we have all even vertices. So we will have an Euler circuit. I challenge you to try to find an Euler circuit through this graph. Remember, you cross each edge exactly once and you start and end at the same place. Now, what about Euler paths? Okay, so if a graph is connected and has exactly 2 odd vertices, then it has an Euler path, sometimes more than one. Any such path must start and end at the odd vertices. If a graph has more than 2, I'm going to be lazy and put greater than 2, odd vertices, it cannot have an Euler path. So again, we want to go through these 3 graphs and say, do we have an Euler path, an Euler circuit, or neither? Each of these is connected, so that part is good. So we need to check the degree of each vertex. This is 2, 2, 2, 2. So this will have an Euler circuit because we have all even vertices. Okay, in the second graph, we have 1, 1, 1, 3 as our degrees. So this will have neither, because it has 4 odd vertices. And our last graph here, we have 2, 2, 3, 2, 3. We have exactly 2 odd vertices, so we will have an Euler path because we have 2 odd vertices. Okay, and again, the Euler path would have to start at one odd vertex and end at the other. So let's go back to Königsberg. Is there an Euler circuit, Euler path, or neither through the bridges of Königsberg? Remember, we drew this diagram in a previous video from looking at the map of Königsberg. So we have 3, 2, 3, 4, 5, 3, and 3. We are going to have neither because we have 4 odd vertices. And that is the conclusion that Euler came to back in the 1700s, was that you could not cross all of the bridges in Königsberg exactly once. So, Euler circuit theorem talks about graphs with no odd vertices. The Euler path theorem talks about graphs with 2 or more odd vertices. Well, what about a graph with 1 odd vertex? What happens then? Well, we have another theorem, Euler's sum of degrees theorem. The sum of the degrees of all of the vertices in a graph is equal to twice the number of edges, and is therefore an even number. So the sum of degrees is even. So because of that, a graph will always have an even number of odd vertices, and it is impossible to have an odd number of odd vertices. So you cannot have a graph with 1 odd vertex. It is not possible. So let's go back to these 3 graphs that we looked at in the previous example. We had already written down the degree of each vertex. So the sum of the degrees is going to be 2 plus 2 plus 2 plus 2, which is 8. How many edges do we have? We have 1, 2, 3, 4 edges. And we have 0 odd vertices. Okay, and you will notice that the number of edges is half the sum of the degree, or the sum of the degree is twice the number of edges. Going on to the next one. The sum of the degrees, 1 plus 1 plus 1 plus 3, is 6. We have 3 edges, and we have 4 odd vertices. Then the third graph here, we have 2 plus 2 plus 3 plus 2 plus 3, which is 12. Our number of edges is 1, 2, 3, 4, 5, 6. And we have 2 odd vertices. So all of these things follow from Euler's sum of degrees theorem. The sum of the degrees is twice the number of edges, and we have an even number of odd vertices. So, in summary, if you have no odd vertices, you have an Euler circuit. 2 odd vertices, you have an Euler path. If you have 4, 6, 8, etc. odd vertices, you do not have either. And if you have 1, 3, 5 odd vertices, that's impossible. You cannot have a graph with an odd number of odd vertices. So now we know when an Euler path or an Euler circuit exists, but you might be thinking to yourself, okay, so how do I find it? Well, this is where Fleury's algorithm comes in. So if you have a small graph, you can probably just do trial and error. But when you have a graph that has hundreds or thousands of vertices, trial and error is going to take you an eternity. So an algorithm helps us find the Euler path or circuit. So first of all, you need to make sure that your graph is connected and has no odd vertices if you're trying to find a circuit, or only 2 odd vertices if you're trying to find a path. Then you need to choose your starting vertex. For an Euler circuit, you can choose any vertex. If you're trying to find an Euler path, you need to start at one of the odd vertices. So, at each step in this algorithm, if you have a choice, do not cross a bridge of a yet to be traveled part of the graph. If that's your only choice, then you have to take it. When you can't travel anymore, the circuit or path should be complete. So either at your starting vertex for a circuit or at the other odd vertex for a path. Basically, bridges are the last step or the last edges that you want to cross. So looking at this guy here, who is trying to walk along this path. So he starts here at F. He is going to walk to vertex C. All right, so we have erased that edge because he has already walked that way. Then we're going to walk to vertex D. Now, he has a choice of whether he goes to A, B, or F next. But this right here is a bridge. He will get stuck and not be able to finish his path or circuit if he walks that direction. So he should not go that way. Instead, he chooses to walk to vertex A. All right, so then he decides to go to C and then to E. Now, basically he just has one big path left. So he is going to go around to A, B, D, and F and complete his circuit. The other place he had a choice of whether to cross a bridge or not was up here. If he had chosen to go to the right, to vertex B, he would have disconnected the graph because that edge is a bridge. So let's go ahead and look at this graph. Okay, we want to apply Fleury's algorithm. So first we need to decide if we have an Euler path or an Euler circuit. So we need to go through and look at the degrees of each vertex. All right, so I have 2 odd vertices. So I need to start at one. I'm going to pick this one, and I need to end at the other one. Okay, so I'm going to start here. I can go any direction. I choose to go this direction. All right, and then I'm going to go down here, this way. Now maybe I'll go this way. I haven't come to a place where I have bridges yet. Let's go this way. This way. And let's go down here and end. Okay, I never really came to a situation where I had to cross a bridge. Let's look at another example. Again, we're trying to apply Fleury's algorithm. So I need to check the degrees of each of the vertices. So I have 2 odd vertices again, so I need to start at one and end at the other. I'm going to choose to start on the right, and end on the left. So if I start here, I'm going to go this way, this way, all right, and then I am done with my Euler path. So that is it for today.